All right, welcome to The Explainer. Today, we're going to pull back the curtain on a hidden chemical principle, a kind of secret connection that links some of the most unrelated things you can possibly imagine.
Yeah, I know. It sounds like the beginning of a really weird riddle, doesn't it? But the answer isn't some clever punchline. It's actually a super powerful chemical concept called coupled equilibria. And believe me, it is quietly shaping our world in some truly mind-blowing ways. So let's dive right in, starting with our oceans.
Okay, so our first stop on this little chemical journey takes us deep into the ocean to look at the fragile foundation of one of the planet's most important and, frankly, most beautiful ecosystems, the coral reef. And you can see the difference right here. It's just night and day. On one side, you've got a healthy reef, a bustling, vibrant underwater city, all built on these strong skeletons of calcium carbonate. But on the other side, well, that's what happens when those skeletons get weak and start to dissolve. The whole place becomes a ghost town, and the very foundation of this incredible ecosystem just crumbles. So what's causing this massive collapse? Well, it's a chain reaction, and it all starts up in the air. First, CO2 levels in the atmosphere go up. Then, that CO2 gets absorbed by the ocean, which makes the water more acidic. Now, this new acid, it's like a magnet for the carbonate ions that corals desperately need to build their skeletons. The acid essentially steals the carbonate right out of the water, making it almost impossible for new coral to grow, and way easier for the existing skeletons to just dissolve away. All right, so let's zoom way in now from the vast ocean to a battlefield that's, a lot more personal. The constant chemical warfare that's happening inside your own mouth. Our tooth enamel is one of the hardest substances in our bodies. It's made of this mineral called calcium hydroxyapatite. It is incredibly tough stuff. But it has one key chemical weakness. And, well, the bacteria in our mouths have totally figured out how to exploit it. Here's how it goes down. Bacteria hang out on our teeth, eat sugar, and then produce acid. Simple enough. But this acid has a huge chemical appetite for something called hydroxide, which is a key building block that holds your enamel together. The acid literally just yanks the hydroxide right out of your enamel structure, totally messing up the balance and causing it to dissolve. And that's all a cavity is, the slow chemical deconstruction of your tooth. So, okay, we've got dissolving coral reefs in the ocean and dissolving enamel in our mouths. They seem like they're worlds apart, right? But as we're about to see, they are connected by the exact same invisible chemical thread. And that chemical thread, that principle, is called coupled equilibria. It's what happens when two different chemical reactions get linked up because they share a common ingredient. When one reaction starts using up a product from another one, that link can completely change the outcome for everybody involved. Let's think about it like this. Imagine a simple chemical balance. An equilibrium is like a perfectly even tug of war. Both sides are pulling equally hard. It's stable. Nothing is really changing at this point. But in coupled equilibria, a second reaction shows up. And it's like this giant hand just comes in and snatches one of the players right off the rope. Poof, gone. Suddenly the balance is completely broken. That first tug of war is forced to shift, and one side starts winning by a landslide, all because the other side lost a key player. And this is where it all clicks into place. Just look at the pattern here. You've got the problems on the left, reefs and teeth. In the middle, you see their main reaction, a solid structure trying to stay balanced. But now look at that column on the right. In both cases, a second coupled reaction with acid comes along and steals a key product. For the reefs, it steals the carbonate. For your teeth, it steals the hydroxide. That theft is what breaks the tug of war, yanking the whole system in one direction and causing the solid thing to dissolve. It's the exact same mechanism. So, this principle can be super destructive, right? But, and here is the really cool part. Once you get how it works, you can actually flip the script and use it to engineer some amazing solutions. This is precisely how fluoride in your toothpaste works. It's using this principle for good. Fluoride comes in and does this brilliant swap. It kicks out that vulnerable hydroxide ion in your enamel and replaces it with a much, much tougher fluoride ion. The new structure, fluoroapatite, is way more resistant to acid because that fluoride doesn't get stolen nearly as easily. It's like you're giving your enamel a chemical shield upgrade. And this isn't some new idea. People have been using this trick for a long, long time. Take old school photography, for instance. To develop a photo, you had to wash away all the unexposed silver bromide from the film. So they used a chemical called hypo, which would couple with the dissolving silver, literally yanking it off the film into a new substance. That's what made the final, clear image pop out from the cloudy negative. So just how powerful is this effect? I mean, are we talking about a small change here? No way. Under the right conditions, coupled equilibria can increase how much a substance dissolves by, wait for it, 10 million times. So here's the bottom line. Coupled equilibria is like a fundamental chemical lever. It's how chemists and nature itself can push and pull reactions in directions they would never, ever go on their own. It can be destructive, like we saw with the coral reefs, or it can be harnessed for some pretty ingenious solutions, like protecting our teeth. It really makes you wonder, doesn't it? From the deep geology of our planet to the crazy complex biology inside our own cells, what other hidden chemical connections are out there, quietly running the show all around us? It's this unseen network of reactions that's a powerful reminder of just how deeply and surprisingly interconnected everything truly is.